we've got another problem up here on the board. This time f of x is this rational function, x plus 3 over x minus 3. And we're going to be finding the derivative, or the slope of the tangent line at 1. And then we're going to find an equation for that tangent line. Okay, now this is a little bit more complicated than the formulas we've been working with so far. So if you're feeling ambitious and want to pause the video and try this on your own, you're certainly welcome to. But I'm sort of assuming a lot of you are going to want to work through this together, and that's totally fine. Now, I like to have a picture, but I don't want to spend a whole lot of time graphing this. Now, I can pretty quickly see that there's going to be a vertical asymptote at 3. And I can also pretty quickly see that there's going to be a horizontal asymptote at 1. Because the end behavior, we're going to be dominated by the fraction of the lead terms, which would simplify to 1. So, with that information, I can get a rough sketch of things. Now, I didn't bother to find exactly where my intercepts were, because I was just getting a very rough sketch of things. But I can get a rough sketch of the graph. The other thing I could do, though, if I wasn't comfortable with what this looked like, is I could say, you know, I just want a place to put my points. Now, at 1, I'm going to get 3 over negative 2. So I'm going to have negative 3 halves. So there's this point here, 1, negative 3 halves. Now, obviously, I didn't draw this super well to scale, but there's my 1, negative 3 halves. And I could just say, okay, this is not an accurate graph. But I can draw something. Now, if I'm going to draw something like that that's so off, I would want to label this as not accurate. Okay? But I'm just using it as a place to put some points so that I can remember the formula by just thinking rise over run without having to memorize something complicated. So I would choose basically a nearby point, and I would label it x, and then x plus 2 over x minus 3. And here I could do the same thing. I could say x plus 2 over x minus 3. Now either way, when I draw in that secant line, I can use the picture to say rise over run is just going to be the change in y over the change in x. What I can't do if I use an inaccurate picture like this is I can't use the picture to double check my answer. This graph, not super accurate, but it's got the right basic idea. I can tell just by looking at the picture that my answer to the derivative should be a negative number because the graph is going down. If I haven't bothered to draw an accurate picture but just drew a random function so that I had a place to put some points, I don't want to assume that the behavior of that random function matches the behavior of this specific function. All right, so f prime of 1 is going to be the limit as x approaches 1 of rise over run. So x plus 2 over x minus 3 minus a negative 3 halves. Of course, that's just going to become plus 3 halves over x minus 1. And of course, I can't plug in 1 because if I did, the bottom would go to 0, and so would the top, because we said that this was going to negative 3 halves if we plugged in 1. Okay, so now I've got this nifty complex fraction. There are a couple of ways that I could work with that. One option would be to just find a common denominator and do this arithmetic, do the addition on top to write that as a single fraction, and then say dividing by x minus 1 is like multiplying by 1 over x minus 1 to get to a simple fraction. What I'm going to do instead, and I don't know that it's any better, might be a little bit faster, I'm going to multiply by 1 in the form of the least common denominator of these internal denominators here. Now 2 and x minus 3 don't have any factors in common, so I'm just going to multiply by their product. 2 times x minus 3 over itself. As long as it's something over itself, that's just 1. But then I can distribute to each piece on top. So when I do that, we get the limit as x goes to 1. Now when I distribute this to the first fraction, the x minus 3's are going to cancel, so that I'll be left with 2 times x plus 2, plus when I distribute to this second fraction, the 2's are going to cancel, so I'll have 3 times x minus 3. On bottom, I'm just going to have x minus 1 times 2 times x minus 3. No need to multiply that out. I'm hoping I'm going to eventually be able to cancel that x minus 1, so I don't want to make the bottom more complicated by doing that multiplication. All right, so we've got the limit as x goes to 1. Let's multiply out what we have on top. Distributing that 2, I'm going to get 2x plus 4, plus distributing that 3, we'll get 3x minus 9, all over x minus 1 times 2 times x minus 3. Limit as x goes to 1. I'm going to have 5x plus 4 minus 9 is minus 5 on top, over x minus 1 times 2 times x minus 3. On top now I can factor out a 5. So this is the limit as x goes to 1 of 5 times x minus 1 over x minus 1 times 2 times x minus 3. And now we can do what we've been hoping we'd be able to do. We can cancel that x minus 1. So we're left with the limit as x goes to 1 of 5 over 2 times x minus 3. Now that there's no longer that x minus 1 on bottom, I can plug in 1. So that's 5 over 2 times 1 minus 3. That's 5 over 2 times negative 2. That's negative 5/4. Okay, so that's our answer to part A. Our slope is negative 5/4. And then part B, we wanted our tangent line. And once again, we've got the information we need to use point slope form. So our point is the point 1, comma, what did we have? We got negative 3/2, didn't we? We plugged in 1. Yes, there we are. That was our point of tangency. Notice this is what we get by plugging into the original function f. Okay. Our slope is f prime of 1, which we've just calculated is negative 5/4. Notice on our accurate, semi-accurate picture, we did have that we were going to get something negative here because the function was going down at this point in the graph. Okay. So now I'm just going to say rise is equal to slope times run, where I'm calculating the rise and the run using my point of tangency and an arbitrary point x, y. So the rise would become y minus a negative 3/2 is plus 3/2, and that equals the slope of negative 5/4 times x minus 1. Again, if you want to choose to simplify that and solve all the way for y, you can. I'm not going to require that you do so. I believe most of the answers to the homework in the back of the book do solve things for y to put things in slope-intercept form. So you may want to do that just to be able to check your answers. But on exams and quizzes, it's totally fine to stop in point slope form.